alkynes. We've treated alkenes, and we said alkenes are single bond, right? Alkenes are single bonded organic compounds. Alkenes are double bonded organic compounds. Then for alkynes are triple bonded. Okay, so let's take down, please put down. Alkynes exist as a family of organic compounds. Alkynes exist as a family of organic compounds which contains a triple bond. Alkynes exist as a family of organic compound which contains a triple bond. Full stop. They have the general molecular formula CnH2n minus 2. They have the general molecular formula CnH2n minus 2 and exhibits the sp hybridization. Remember, I told you that alkanes exhibit sp3 hybridization, alkenes sp2. Then we are saying that as for alkynes, they exhibit sp hybridization. I made mention of hybridization and I said that hybridization has to do with the formation of new orbitals from previously existing orbitals. I told you that orbitals are areas in an atom where electrons are formed. Areas, positions, sites in an atom where electrons are formed. So we are saying that the first thing is that they are families of organic compounds containing triple bond, that's 3 bonds. They have the general molecular formula of CnH2n minus 2, and their hybridization method is sp hybridization. Now in this triple bond, please put down. Now the triple bond contains 1 sigma bond and 2 pi bonds. 1 sigma bond and 2 pi bonds. So the first bond is the sigma, the second is pi, the third is also pi. Is that okay? Do you understand? Alright. So quickly, I want you to understand also that alkynes exhibit certain kind of reactions. Okay? So please put down examples of reactions exhibited by alkynes. Examples of reactions exhibited by alkynes are: number 1, we have the addition reaction. We have elimination reaction. We have substitution reaction. Then we also have combustion reaction. I told you that combustion reaction is peculiar to all hydrocarbons. And don't forget what we mean by combustion reaction. That is a reaction in which an organic compound or a hydrocarbon burns completely in the presence of oxygen gas to liberate carbon dioxide and water. Very important to take note of that. Another thing we must take cognizance of are the members of the alkene series. But before that, let us look at the physical properties of alkynes rather. We are looking at alkynes. So physical properties of alkynes. Please write paragraph. Okay, alkynes exhibit physical properties. Alkynes exhibit physical properties such as number 1. Alkynes exhibit physical properties such as number one. Now they increase their boiling points. They increase their boiling points based on an increase in molecular weights. They increase their boiling points based on an increase in what? Molecular weight. That's number 1. Molecular weights, that's number 1. Number 2, based on an increase in molecular weights. That is that their boiling point is increasing. It is because of the increase in molecular weight. So the more the molecular weight, the more the boiling point, or the higher the boiling point. Number two, they show a sweet smell which is faint. Compared to alkenes. That is their odor. Show a sweet smell which is faint compared to alkenes. I told you that alkenes also have a sweet smell, right? But both of them are actually faint. For alkenes, they are more like they are odorless. But you see alkenes, you see alkynes, they exhibit sweet smell. but very faint. Very what? Faint. Are we together? Are we together? Now, number three, put down. Alkynes are known to be insoluble in water, but soluble in fatty solvents. To be insoluble in water, but soluble in fatty solvents. Okay? But soluble in fatty solvents. Are we together? So they can dissolve only in fat, but they cannot dissolve in water. That's what we mean by insoluble. They cannot dissolve in water. Number what now? Number four. Alkynes increases in melting point. Alkynes increases in melting point with an increase in molecular weight. So it is similar to boiling point. As molecular weight is increasing, boiling point is increasing. As molecular weight is increasing, melting point is also increasing. Alkynes increase in melting point with an increase in what? Molecular weight. Are we together? Alright, full stop. Now let's look at nomenclature of alkynes. Nomenclature of alkynes. How can we name alkynes? How can we name alkyne structures? Are they similarly named as others, or there is a variation, there is a difference between naming alkynes, alkenes, and alkanes? Now please put down. Now alkynes are named according to the general rules. Alkynes are named according to the general rules of nomenclature. Alkynes are named according to the general rules of nomenclature. Full stop. However, after the determination of the longest continuous carbon chain in the structure, the carbon containing the triple bond is given the smallest possible number. However, the carbon containing the triple bond is given the smallest possible number. That is after you have gotten the longest continuous carbon chain and you want to start numbering the chain, you must ensure that you number from the end that will give the triple bond the smallest possible number. That's why we say, however, the carbon containing the triple bond is given the smallest possible number. This is similar to what we did in alkenes. Is that okay? This is similar to what we did in alkenes, where we gave priority first to the carbon containing the triple bond before we went further to consider the substituents. And I told you that whenever you come from both ends and the carbon containing the triple bond has the same number, that is the only time you should consider the substituent. Is that okay? That's the only time you should consider the substituent. Is that okay? Alright. Now, full stop. Now the parent name of alkynes, follows the suffix YNE. So what we are implying is that if we have ethane is being called ethane because it is from the alkane family. ANE is the suffix. Ethene is called ethene because it is of the alkene family. The suffix is ENE. Then we are saying that for alkynes, we will have ethyne. We have what? Ethyne. Are we together? So it is because of the suffix what? YNE. So every member of a given homologous series carries a nomenclature that ends with the suffix of that series. Do you understand? Is it clear? Alright, let us proceed. Okay, so now please write the first few members of the alkyne, right please. The first few members of the alkyne series are as follows. So the first few members of the alkyne series are as follows. Now, first of all, the first member of the alkyne series is called ethyne. Ethyne is also known as acetylene. It's also known as acetylene. And ethyne is a hydrocarbon that has general molecular formula C2H2. Now let me explain how this C2H2 came about. The general molecular formula for the alkyne series is CnH2n minus 2, am I correct? Yes. So if we have N and we agreed that N is the number of carbon atoms, then let us do the math. Now if we are to do the math here, it means that if we have C2 here, it will be C2 times what? 2 minus what? 2, right? So 2 times 2 is what? 4 minus 2 is what? 2. So that's how we have what? C2 what? H2. Are we together? Then now the structure is like this. We have CH triple bond CH, close the bracket. So that is the structure of a typical alkyne, which is of course an example of that ethyne. Now we also have propyne. I told you that whenever you hear propyne or prop, regardless of the suffix, please note that we are always talking about a hydrocarbon that has how many carbons? 3 carbons. Please don't forget, prop. Don't forget. So this is C3H what? C3H what? 6. Is it 4 or 6? Is it 4? It's not 3 times 2. It's not 3 times 2. And we have 2 times. It's not 3 times 2 in this case. What are we supposed to follow? The formula, right? Good. So you're on track. So it is C3 what? H what? C3H4. Now I want you to understand that generally hydrocarbons in the different series tends to increase by 1 carbon and 2 hydrogens. They increase by what? And how many hydrogens? 2 hydrogens. If you remember alkanes, methane is CH4, ethane is C2H6, propane C3H8. You will realize that it's increasing by 1 carbon and 2 hydrogens. So C3H4 will be like this. We have our CH triple bond, we have C single bond, then we have CH3. This is propyne. This is propyne. Okay? Now, if you remember when I taught you how to write a structure or draw a structure correctly, you remember or realize that when we are drawing structures, we have to take cognizance of the number of bonds so we can be able to write the structure well. The reason why we have only 1 hydrogen here is because we have 3 bonds. Normally, a carbon is supposed to have how many hydrogens? 4 hydrogens, right? Now, whenever you remove 1 hydrogen and you create a carbon-to-carbon what? Bond, how many hydrogens will remain? 3, right? If you decide, okay, no, let me put another carbon here, how many hydrogens remain? So if you look at it very well, you realize that the bonds, the more the bonds, the lesser the hydrogens. Alright? Now if you look at this carbon at the center, you realize that it has how many bonds? 1, 2, 3, 4. That's why there's no hydrogen left. Are we together? That's why there's no hydrogen left. Now, number 3, we have what? Butane. Whenever you hear boot, please, it's not shoe boots. It is 4 what? Carbons. 4 what? Carbons. Alright? So this is C4H what? 6. So this will be CH, 1, 2, 3, triple bond. We have our C, single bond, CH2, then CH what? 3. The list is actually long, but like I said, we'll be looking at the first few. Let's look at the first 7 members, alright? The first 7 members, so we can just look at the first 9 members at home. Alright? Okay. Now, butane is this. Then we have pentyne. Pentyne is C5H what? 8, right? Which is CH, triple bond, C, single bond, CH2. Okay? Do this. CH2, then you write 2 outside. Is that okay? Then what? CH what? 3. This is a condensed way of writing it. This is a condensed way of writing CH2, CH2. Because at this point, it will be increasing by CH2. It will be increasing by what? CH2. Then the next one is hexyne. Hexyne is C6H10. So we have CH, triple bond C. Then our CH2 having what? 3, right? Then CH what? 3. Then we have heptyne. Heptyne is C7H12. We have CH, we have C, CH2, 4, CH3. Are we together? Then when we have 8 carbons, it is octyne. Octyne is C8H14. So we have CH, C, CH2, 5, CH3. Alright? So then we have nonine. Nonine is C9H16, CH, triple bond. Then we have our C, CH2, we have 6, CH3. Then lastly, decline, we have C10, right? C10H18. So we have CH, C, CH2, 7, then CH3. So these are the members from 2 carbons to 10 carbons. Are we together? From 2 carbons to 10 carbons. And it's very important to know how alkynes can actually be named. Like I said, they all follow the general rules of nomenclature. However, when it comes to numbering the chain, please number from the end that will give the carbon containing the triple bond the smallest possible word number. That is the idea. That is the idea. Are we together? So now let's proceed. Okay, let's proceed. Now, please put down. Put down. All right. So we'll be looking at the concept of nomenclature, in which we'll name various structures. All right. So let us name the following structures. Okay. So we have this. Now, there is a specific method of, let me leave the lines. This is a line structure. Okay, let me leave one line structure, then let me add the one that is in the structural formula, having the number of carbons here, okay, and the number of hydrogens fully displayed. All right, then here we have C, single bond, then we have C, Cl here, CH2 and CH3, then CH3 at this point. That's number 2. Then number 3 is CH3, C, CH2, CH2, C, CH2, CH3, C, triple bond to C again, single bond to CH2, then CH2, CH3. All right. Then at the top here we have B, we have Br. Okay. Then here at this point we have a double bond here. Then we have another bromine here, Br. So we'll be looking at these 3 structures. These are number 1, these are number 2, these are number 3. Now, if you look at number 3, you realize that we are having a double bond and a triple bond. Are you seeing that? Yes, we can have a double bond and a triple bond in one structure. It's like that. Yes, it exists. Yes. All right. So by the time we are done naming the line structure, we'll come to this and to this. Now, there's something I will explain in this line structure. There's something I will explain in this line structure that will look a little bit different from what we have been doing in other line structures. Will look a little bit different from what we have been doing in other line structures. That is the skeletal structure. That's what I mean by line structure. And I need you to remember it at all times. Now, it will only apply for alkynes in line structures or skeletal structures. It will not apply in these 2 cases. Are we together? All right. So let us quickly read structures. And like I said, what I will explain in this line structure would not be similar to the skeletal structure here. Just pay attention to that. Now, you know, the first thing we have to do when we are naming a structure is to count the longest continuous carbon chain. Do you agree with me? Yeah. You count the longest continuous carbon chain in the structure. Now, look at this. When we are counting, we count from here 1, 2, 3, right? Are we together? Now, when we get to the position of the triple bond, you see this point here. I see this point. This point is a carbon for triple bonds in line structures. So we say 1, 2, 3, 4, then 5, 6, 7, 8. So the last point of the triple bond in the line structure is a what? Is a carbon. If we are not counting from here, it will be 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. But in the regular one, it is 1, 2, 3, 4, 5. Or 1, 2, 3, 4, 5, 6. Is it clear? So what I'm saying is that in this one, when you're counting, the point on the double bond is a carbon. The point on the double bond has a carbon there, carbon atom there. So if you count 1, 2, 3, then 4. The last point of the double bond from the angle you are counting. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. It's technical, but it's something that is easy to understand. Is it clear? Do you understand it? Yes, it's easy. 1, 2, 3, 4, 5, 6, 7, 8. 1. If you want to count from here, 1, 2, 3, 4, 5, 6, 7, 8. Ask a question. Just alkynes. Just alkynes. It only works for alkynes alone. You can't do that to alkenes. Alright? It's because of the triple bond that we have that carbon attached at the point there. And it's only for line structures. Only for line structures. Are we together? Alright, I will expatiate on this more, okay, in subsequent classes where we'll start looking at exam questions. But now let's look at this. So if you want to name now, the longest continuous carbon chain is from here to here, right? Yes. That is 9 carbons. So now the thing is, the idea is this. We count from the side that will give the triple bond the smallest possible number, right? Yes. So now if we are counting, it will be 1, 2, 3. This is a carbon, don't forget. This is also a what? Carbon. This is also a what? Carbon. So if we are counting, we count 1, 2, 3. So at this point, the triple bonds are carbon what? If we count from here, 1, 2, 3, 4, 5, 6. From here, the triple bonds are carbon what? 6. But if we are counting from here, it is 1, 2, what? 3. Right? So which one is the smallest? 3, right? Good. And if we count 1, 2, 3, 4, 5, 6. This is ethyl, is it not? Yes. Because ethyl is because it has two what? Two carbons. It has 2 carbons, it has 2 ends. This an end, this also an end. Alright? So it means that we have ethyl at carbon 6. So the name of this structure will be what? 6 what? Ethyl. Now how many carbons are in the long chain? 9, right? So we say non. Non what? 3 what? Ion. Non 3 ion. The reason why it's non 3 ion is because the triple bond is at carbon 3. Alright? That's why it's non 3 ion. Now for the second structure, let us quickly look at that. For the second structure, we will not do it the same way we did for the line structure. We'll just count the number of carbons. Alright? So now look at this, guys. So 1, 2, 3, 4, 5. The straight chain is having 5 carbons, right? Yes. But it's not the longest. Now, I believe like this is the longest, right? 1, 2, 3, 4, 5, 6. So it means that from here to here is the longest. So it means that this and this are what? Substituent, because they are not part of the parent chain. In a structure of alkyne where we have 6 carbons, what's the name? Hexyne. Hexyne, not heptine. Hexyne. Alright? So 6 is hexyne. And we have to number from the end that will give the triple bond the smallest possible number, right? We start from here. The triple bond will be at carbon what? We start from here to be 1, 2, 3, what? 4. But from here it's at carbon 2. Alright? So it means that we are numbering from here. We say 1, 2, 3, 4. No, this is 4, right? Then 5 and what? 6. Okay? 5 and 6. Numbering from here now has given us the position of the substituent. If you look at it clearly, you realize that both substituents are carbon 4, right? So alphabetical order, chloro comes first, right? So this will be 4 chloro, 4 what? Methyl what? Hex what? 2 what? Ion. H2 ion. Okay? Because The triple bond is at carbon 2. Now, let's look at the third structure. For the third structure, we are having the longest continuous carbon chain from here down to here. Am I correct? Am I correct? The triple bond is here. Then there's also a double bond here. And I told you that in a structure like this, we can have a double bond and we can also have a what? Triple bond. Okay? But look at how I'm going to explain this. Please pay attention so you will not miss out on this. Now, if we have been able to ascertain that this is the parent chain, like this is the parent chain. Now, this is a substituent, this is a substituent, this is also what? A substituent. Now, how do we navigate through this? How do we navigate through this? Alright? So, we are to name this by, first of all, in the structure, the carbon containing the double bond will have a smaller number than the one containing the triple bond. That is the rule. Start from the end that will give the what? Carbon containing the double bond a smaller number than the what? Carbon containing the what? Do you understand? In this case now that we're having a double and a triple bond, you start from the end that will give the what? Carbon containing the double bond the smallest number. And you agree with me that it is from here, right? Yeah. So now if you number from here, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, and what? 10. 10 carbons will be decyne, right? Decyne, right? Beautiful. But normally, 10 carbons is decyne when you have only what? Triple bond. But we have something like decyne. Decyne. Now look at this. What do I mean? Now, how many substituents are here? 3, right? Now let us write the name first. You know, we have to start by naming it with the substituent first, right? Good. In alphabetical order, bromo comes first before ethyl, is it not? Now, bromo is at carbon what? 2 and 5, right? So we say 2, 5 what? Die. Not that you should die, you. Die meaning that we have what? 2. So don't just say 2, 5 bromo. 2, 5 means that you are having 2 carbons at 2 positions of 2 and 5 respectively. 2, 5 dibromo. Ethyl is at carbon 5, right? So 5 ethyl. Now look at this. We have 10 carbons, right? So now we say dec. The double is at carbon what? Dec 2 in 6 what? Iron. Shikina